It's my pleasure to introduce Frederick Chen. Frederick received his degrees at MIT. He has held positions at MIT Lincoln Laboratory in addition to his current position as senior scientist at the Signal Systems Corporation. He is a senior member of the IEEE, and something that he didn't include in his bio is that he's also has basically been born with a gift of a broadcast quality voice. So he has one of the best voices in the community, and with my pleasure, I'd like to introduce Frederick Chen.
Thank you, David, for that very kind introduction. It's an honor to be an invited speaker, and I hope that my presentation will live up to that honor. So I'm going to be talking about neural networks and satellite-based atmospheric remote sensing. I did a bit of work with satellite-based remote sensing when I was a graduate student at MIT, and then for a few years after that at MIT Lincoln Laboratory. I'm going to first start off by giving the background on the research, and then talk about some of the challenges for atmospheric remote sensing algorithms and how neural nets can address those challenges. I'm in particular going to talk about how signal processing together with neural nets can help us to come up with efficient algorithms for remote sensing. And then I'll talk about the specific applications that I and some colleagues have worked on, and then end with some conclusions. The work done in this talk was done in support of the Joint Polar Satellite System. It used to be called the National Polar Orbiting Operational Environmental Satellite System, NPOS for short. It's a collaborative mission between NOAA and NASA and represents the next generation of NOAA's polar orbiting environmental satellites. This effort represents a significant technological and scientific advance in environmental monitoring. This program supports the 9 societal benefits identified by the NASA Earth Science Division for its Applied Sciences program. So some of the societal benefits include improved weather forecasting, disaster planning and management, ocean resource monitoring and protection, climate studies, sustainability, and so on, things that are very relevant to daily living. Here are some of the products that are going to be produced by JPSS, and some of them are already being produced by the SWOMI NPP, the SWOMI NPOS Preparatory Project, which was a risk reduction mission for JPSS. So there are various cloud properties, temperature and moisture profile, precipitation type, sea surface wind speed, a variety of atmospheric and surface variables. There are several different challenges for remote sensing algorithms. One is the large amount of data. You may remember from this morning that David Johnson talked about the fact that there's been an exponential growth in the amount of data you can collect. The same is true in the world of weather satellites. About 10, 11 years ago, the NASA Aqua satellite was launched, and it provided a data flow of about 89 gigabytes per day. I would be surprised if that number has increased to about the order of a terabyte per day. So we have a lot of data to deal with. So we need computationally efficient algorithms to put out our products in a timely fashion. We also have to deal with the highly nonlinear physics of the atmosphere. First, I'm going to talk about the amount of data and computational efficiency. Some of the critical issues include being able to provide atmospheric variables globally with satellites. We can produce products locally over a specific area, but we want to be able to do it globally because the Earth is one huge system. What happens in the poles can be influenced by what happens over the intertropical convergence zone near the equator. And what happens over land obviously is affected by what happens over sea as well. So we want to be able to create a global picture of what's going on in the atmosphere. We want to deliver high-quality satellite-based products in a timely fashion. There are some applications where timing is absolutely critical, like nowcasting, which is forecasting 3 to 6 hours in the future. If your nowcasting algorithm takes 12 hours, well, it's pretty much useless. On the other side of the spectrum, where we're looking for information on what happens over a long period, we're going to have to process a lot of data, and we may want to do it multiple times. So we're definitely interested in fast algorithms. So let me talk about the improvements that have taken place in satellite-based instrumentation over the last several decades. I'm going to talk about spatial resolution and spectral resolution. On the left, we show the progress in spatial resolution over the past 40 years. In red, we show the improvements for microwave, and in blue, we show the resolution for infrared instruments. So over the last 40 years, microwave instruments have experienced about a factor of 3 improvement in spatial resolution, that is, in each dimension. Infrared instruments have experienced an improvement of about a factor of 2. Oops. What just happened? My apologies. Okay, so on the right we show improvement in spectral resolution. Microwave instruments have experienced an improvement of about a factor of 4, and infrared instruments have experienced an improvement of a factor of about 300. That's very good. What are the advantages of that? We can create more accurate retrieval products, and we can do remote sensing over a much finer scale. We can see fine structure that we wouldn't be able to see at very coarse resolutions. But the downside of that is that there's a very large amount of data that we have to process. Now I'll talk about the nonlinearity problem. So here's a picture of the atmospheric remote sensing measurement scenario. The satellite-based instrument measures thermal radiation, and that typically originates from the sun and to some extent from the Earth as well. As the thermal radiation travels downward through the atmosphere and back up, it goes through emission, it goes through absorption, and also some scattering. So what you end up seeing here is a very highly nonlinear function of temperature profile and other variables that you might be interested in. There are 2 general classes of approaches to atmospheric remote sensing algorithms. The first is called the variational approach, where we have a forward model that relates the atmospheric state to the sensor measurements. And when you, in the variational approach, typically what you're going to do is to take a guess at the atmospheric state, and then run it through the radiative transfer model, and then just keep doing that until you keep adjusting your guess until you end up with a solution that gives you something that matches your observations pretty well. The second approach is a statistical or regression-based approach, where you are taking your ensemble of observations and atmospheric state variables and deriving a statistical relationship between the 2. Currently, operational algorithms tend to rely on the radiative transfer algorithms, which is the forward model, and these are computationally very intensive. Typically, radiative transfer algorithms use polynomial approximations. In the future, however, radiative transfer algorithms could also combine some of the statistical strengths of neural networks. So what are the advantages of neural networks? They're fast and simple. Their computations involve only elementary functions. So neural net-based algorithms could be run in real time. Another advantage is that neural nets don't require any a priori assumptions about the statistics of the data. You don't need to get it into some form like join the Gaussian or whatever. You can just take the data as is, run the neural net training on it, and derive a statistical relationship. But one critical issue in neural net learning is pre-processing and to some extent post-processing. Typically, your data is not going to be in a form that neural nets can learn with very easily. So you do some pre-processing to transform it into something that makes it easier for the neural network to learn. And in this talk, I'm going to be talking about how we use signal processing and image processing methods to do our pre-processing. We do some spectral signal processing, that is signal processing across the spectral domain. We also do some image processing, and we also have the stochastic cloud clearing method. I'm going to talk about the estimation of temperature and water vapor profile using the an infrared sensor, the Advanced Infrared Sensor. This was developed by Bill Blackwell at MIT Lincoln Laboratory. I'm also going to talk about the estimation of precipitation rate with the Advanced Microwave Sounding Unit, which I developed with the late David Staley. Here's a look at the retrieval of temperature from infrared and microwave data. AIRS data gets fed into stochastic cloud clearing, and the results of that get put through projected principal components. And then that reduces the dimensionality of the data, and the result is fed into the neural net, which estimates temperature profile. We definitely need to do pre-processing of our infrared data. And the reason is that we have over 2,000 channels, so we need to do dimensionality reduction, and we also need to deal with the clouds because they corrupt AIRS temperature and water vapor profile products. The first pre-processing step is stochastic cloud clearing. The advantage of this is that it involves only matrix multiplications, so it's faster than current operational cloud clearing algorithms. And then the second part of the pre-processing is projected principal components, and we'll talk about that a little bit later. It's one of the variations on principal component analysis. When we first talk about stochastic cloud clearing, here's a block diagram. We have AIRS radiances, and we also have some microwave data. And we use that, we select cloud-free pixels, and then feed all of this into a linear operator to get a preliminary cloudiness metric. And then we put that data through linear operator B to get another a more refined cloudiness metric. This gets put through a decision where we divide the fields of regard into less cloudy and more cloudy. Less cloudy fields of regard are sent to this linear operator that produces the cleared brightness temperature. And then the more cloudy fields of regard are sent to the linear operator D. That has not yet been implemented. So how does the stochastic cloud clearing do? So here we have a look at the cloud clearing errors as a function of altitude. The errors level 2, the operational product, the errors are shown here in black, and the stochastic cloud clearing errors are shown in blue. And you can see that the performance of SCC approaches that of the operational product. And one thing that's noteworthy about this is that the errors for the operational product have been computed using only the 7% of the fields of regard that were accepted. The errors for SSC, shown in blue, were computed using 27% of the fields of regard. So with the stochastic cloud clearing algorithm, we've been able to get a fourfold improvement in our data yield. That is the amount of useful data that we can use for other purposes. Here's a look at what stochastic cloud clearing does from a visual perspective. Up here we have the observed brightness temperatures or radiances, and we can see in this image that there's quite a lot of cloud cover here. That's going to present a problem when you're trying to do temperature profile estimation. When we apply stochastic cloud clearing to that, most of these clouds have gone away, and they actually look pretty close to the background of what we see here. At the bottom, we have an image of sea surface temperature. And when we compare these two images, we can see that this has produced something that is quite plausible. And on the right, we see the same thing. Heavy clouds get cleared from the image, and what we get shows a comparable shape to the sea surface temperature. Now we'll talk about projected principal components. First of all, some of you may be familiar with principal component analysis as a dimensionality reduction method. PCA is an unsupervised method. Its principal components depend only on data being decorrelated. There is no target that PCA is trying to mimic. So your dominant PCs are not necessarily correlated with your target variable. On the other hand, projected principal principal components, which I'll abbreviate as PPC, is a supervised method. Its PCs are derived to maximize correlation to the target variable. So PPC is more likely to be useful than PCA. So how do these methods compare? First of all, I'm going to talk about how these methods can be used to reconstruct the errors of noise filter gradients data. And I think the colors, I apologize if the colors don't come out that clearly. Even from here, it's a little bit hard to see. So we're comparing principal components with noise-free PC, noise-adjusted principal components, PPCR, that's PPC targeting radiances, and PPC targeting temperature. So there's a pretty good divide between PPC for temperature and everything else. And we can see that all the other methods, for all the other methods, as you add principal components, the error goes down quite a bit and reaches the theoretical limit around maybe about 40 or 50 principal components. PPC for temperature, on the other hand, doesn't show that sort of improvement. The error doesn't go down very quickly. So does that mean that that method is useless? Well, the question we're trying to figure out is how well can we estimate temperature profile retrieval? So we're going to do the same experiment, but we're going to do an experiment where we're reconstructing temperature profiles. And now the tables have been turned. PPC for temperature reaches the theoretical limit with around 20 principal components. All the other methods take about 100 principal components to achieve the same error. So how does the neural net-based method do relative to the operational product that runs the radiated transfer algorithm? Let's first look at these two red curves. The errors level 2, the operational algorithm, the results are shown in this dotted line, and the MIT algorithm using neural nets is shown in this solid line. And we can see that the estimation error with respect to balloon sounding data, the errors for the two methods are pretty comparable. And I need to clarify that we're looking at data for which the quality bot flag is set. That means that the estimates are considered to be reliable down to the lowest parts of the atmosphere. So another question we can ask is what happens when we decide to compute the errors over all fields of regard, including those that might not be quite as good as the quality bot flag indicates. And when we look at these two errors in blue, where we're looking at all the data, we can see that the neural net algorithm is comparable to the operational product, and even does a little better between the altitudes of, well, these are expressed in pressure actually, but there's a range of altitudes for which the neural net-based algorithm does better. I'm not going to say that the neural net algorithm wins hands down, but at the very least, I will say that the neural net-based algorithm does at least as well as the operational algorithm. And another thing to note is that the neural net algorithm is less sensitive to the cloud amount. Here we plot error with respect to cloud fraction, and up to this point, where we have a cloud fraction of about 0.6, the errors are comparable. But then as you go towards the more cloudy fields of regard, the operational algorithm starts to do significantly worse. So the stochastic cloud clearing portion of this neural net algorithm gives us an algorithm that's much less sensitive to cloud amount. So how long does this take? After all, I did mention that one of the things we want is a fast algorithm. One granule of errors data that covers about a 2,000 by 2,000 kilometer area can be processed in about 1 second, and that is about 100 times faster than the errors operational algorithm. So in summary, the neural net algorithm gives results that are comparable in accuracy with the operational product. It provides a higher yield. It's not as sensitive to cloud fraction, and it's also quite a bit faster. Now I'm going to talk about the estimation of precipitation rate. Here's a block diagram of the precipitation algorithm. We have microwave data, we have auxiliary data like land sea boundary data. This gets sent into a signal processing module, and then the outputs get fed into a neural network that then estimates precipitation. What kind of signal processing do we do? We have some neural net-based corrections of angle-dependent variations in brightness temperatures. We have some precipitation detection. We do cloud clearing using regional Laplacian interpolation. We do principal component analysis to reduce the dimensionality of the data, and we also do some image sharpening. Here's a look at some AMSU data. This is Hurricane Isabel from 2003. We have a surface-sensitive channel that is, it sees all the way to the surface, in this case, ocean. And then we also have channels with varying degrees of opacity. These are three 183 gigahertz channels. They straddle the water vapor resonance line. And as you move closer to the water vapor resonance line, the channel sees higher and higher into the atmosphere. Here's a more detailed look at the algorithm. At the top left, we have precipitation detection. Here we have some crop data detection, limit surface correction, regional Laplacian interpolation, image sharpening, and the outputs of this part of the algorithm include precipitation-induced cold perturbations at 54 gigahertz, the oxygen resonance band, at 15 and 50 kilometer resolution. And we also have precipitation masks at both resolutions as well. Here's the second part of the algorithm. We have 54 gigahertz precipitation perturbations at 15 kilometers. We have temperature profile principal components, water vapor profile principal components, some water vapor channel data, and the secant of the satellite zenith angle. The outputs of these are fed into the neural net, which then estimates precipitation at 15 and 50 kilometer resolution. I should note that this neural net actually does not estimate precipitation, but there is an additional post-processing step. So this is actually estimating something like the log of the precipitation. Why do we do that? Because precipitation varies over a large range of scales. You can have light precipitation at around 0.1 millimeters per hour. You can also have tropical downpours on the order of 100 millimeters per hour. When you train your data, if you're not careful, you could end up letting your tropical downpours overwhelm the training. That's why we, instead of rain rate, we have the neural net estimating the log of the rain rate. And that is, I talked a lot about pre-processing, and here we have a need for post-processing as well. This is a look at the limit surface correction. On the left, we have an image of some 54.4 gigahertz data, and this instrument is a cross-track sweeping instrument. So naturally, we're going to have some angle-dependent variations, and for this channel, the brightness temperature gets colder as you go out to the more extreme angles. And we want to do something to the data. We want to flatten it so that the result is what you would be seeing if you were able to look directly downward at all of those pixels. And when we apply a neural net correction, that is, we trained a separate net for this purpose, we do see that this has indeed been flattened. We trained a net to estimate the nadir viewing brightness temperatures. And now that we've flattened it, we're able to see these cold spots that we were not able to see over here. Here's a look at the precipitation detection algorithm that we used. We used data from the 183 gigahertz band. And when we apply this to this image, there are a bunch of red spots over here. We can see that we have something that could look like a precipitation map. It looks like it has the shape of precipitation. We also have used cloud cleared data to get an indication of cloud-free conditions surrounding precipitation. And we also use it to produce a perturbation image, and that gives us an indication of the heights of precipitating clouds. here's a look at the cloud clearing results. Before cloud clearing, we have this, and then after cloud clearing, we have something that doesn't show the signatures of clouds at all. We do some image sharpening. Because of time, I'm going to speed through some of these slides. Here's the 183 gigahertz data at 15 kilometer resolution, and we're going to try to force the spatial characteristics of this onto this 50 kilometer image. And here's what we get. And we're able to take information from the coarse resolution channels and use it to do estimation at fine resolution. We do principal components to characterize the temperature profile and also the water vapor profile. And for the water vapor profile PCs, we use a method called constrained PCA because some of those channels are sensitive to the surface. Basically, we're computing surface-sensitive PCs and then filtering them out of the data. We're projecting our data onto the surface-sensitive PCs and then eliminating them from the data. There's also some topological preprocessing involved. I'm not going to go through that because of time, but atmospheric variables depend on the time of day and the season, and you don't want to just use them just a one-dimensional time of day. You do want to transform it so that there is some continuity across your problem areas, like midnight, or in the case of geolocation, the North Pole and the International Dateline. I must have hit a wrong key, my apologies. Okay, so here's a look at the precipitation retrievals. Here's a look at NexRad ground-based radar data at 15 kilometer resolution, and here's the same thing from our neural net-based algorithm. And we can see that they both agree on where it is raining, and also both agree on where it's heavily raining. And here's an example of the global application. We definitely see that our algorithm produces something that's plausibly like precipitation. I'm not going to say too much about the accuracy over oceans because we didn't train over there. And in summary, we've seen that neural network retrieval algorithms can be used to do atmospheric profiling and precipitation estimation. Neural networks offer several advantages over traditional approaches like speed, simplicity, flexibility, and accuracy. And then I also want to re-emphasize that pre-processing is critical to neural network learning. And in this presentation, I've talked about signal processing and image processing for that purpose. Just want to acknowledge, I just want to mention that the work that I've presented here had its origins in the MIT Remote Sensing and Estimation Group, led by the late David Stalin, who passed away about 2 years ago. The work continues under Bill Blackwell at MIT Lincoln Laboratory. He developed the temperature profile retrieval algorithm. I developed the precipitation algorithm. Chuck Cho developed the stochastic cloud clearing, which I talked about before during the part on temperature profile estimation. And Chinewat Surasavadi of the Prince of Songkhla University in Thailand has continued the precipitation work. And if you would like to know more, Bill Blackwell and I wrote a book called Neural Networks in Atmospheric Remote Sensing, which was published about 4 years ago. And here's a sample of some of the papers from the MIT Remote Sensing and Estimation group. Thank you very much for attending.
It's time for questions. I'm sure you will.
I'm aware that Gaussian processes are well spread, have been used a lot for geostatistics.
That what has been used for
Gaussian processes.
What processes?
Gaussian
processes have been used for geostatistics.
Right, and at the same time, I understand that if you take a neural network, you fix the input and output, and you get the inner layers to the instinct, you got a Gaussian process, or a collection of Gaussian processes. So I wonder is that whether you, at some point, thought of using Gaussian processes as well, or?
That's new to me. Could you just briefly explain how Gaussian processes work?
Well, The idea is that if you have, let's say, the Earth, and you map, you get each. Let's say you have the map completely flat, and you can assume that at any point when you fix a point in the map, the target value you will obtain associated to that point will be a Gaussian distribution, Gaussianly distributed. But when you have the set of points, then it's an infinite map, okay? But you just have a grid on it on the map, and the joint distribution of all the points in the map are. I'm sorry, not the joint. For each point you have a function, right, associated to it. That is the value that we're observing associated to that point.
Okay.
Well, all the f values that will target values you will observe from the collection of your points in the map has a joint Gaussian distribution as well.
Okay.
And that process has been proved to be the limit of an infinitely large neural network.
Okay. So you're saying that the errors are a Gaussian process, or that the outputs are a Gaussian process?
The output will give you the estimated value that you get from the neural network, and besides that will give you the certainty associated with the prediction that you don't have with the neural network. I just don't know about the complexity in terms of computational complexity, how we compare to the neural networks.
I'll have to think about that.
But that
I
would be
haven't yet.
the point together.
I hadn't heard about Gaussian processes. Thank you for your comment.
I had to ask, when you say the operational algorithm, is that what we get from NOAA? Is that what they're using?
Right.
So that's what does our weather forecasting?
I don't know exactly what. I would like to. I think that it is used in weather forecasting. Don't quote me on that. That is certainly the intention. You know, we develop atmospheric products not to just continue doing testing on it, but we do want to get that into the real world.
All right, that's good. Thank you.